In the last video, we went over the derivation of the Henderson-Hasselbalch and the assumptions that we could make, what we needed to know in order to use that equation. So I just want to kind of emphasize the concepts behind a buffer. And I've mentioned it before when we talked about the pH of blood. I said that blood resists the change of acidity, so its pH stays pretty darn constant. And that's for a good reason, because that's how we survive. And I called that a buffer. Well, that's exactly what a buffer is. So the gentleman in the picture, he's about ready to do a belly flop. I don't know why he's choosing to do this, onto what look like a bunch of pillows. I wouldn't suggest it. I would expect something bigger and poofier before I would do such a belly flop. But the pillows are going to soften the blow as he lands, not stop it. So I'm thinking he's going to regret his life choice once he hits, but he's not going to be as hurt or injured or in as much pain if those pillows weren't there. So that's all a buffer does. It doesn't prevent the changes, it resists the changes. So if I add an acid or a base to a buffer, I am going to get only a small change in pH, but I will change it. What do they have to be made of? Well, the formic acid example was the demonstration of that and the actual equation that we came up with. Because remember, we had the log involved of the HA and the A minus. So that means that I have to have a weak acid and its conjugate base, or a weak base and its conjugate acid. So I think I just answered this. If I add a small amount of a strong base to a buffer solution, what's going to happen? Well, the pH is still going to increase, but just not as much. Just not as much. And what happens if I add, what happens if my computer cooperates? Oh, cooperated all at once. Here we go. So if I add a strong buffer to, a strong acid to a buffer solution, what's going to happen to the pH? Well, just like the pH of adding the strong base to the buffer solution, the strong acid to the buffer solution is still going to decrease the pH, but not as much. So a strong acid, what's it going to react with? Is my acid going to react with the water, with the HA, or the A minus? So let's think about that. In this solution, I have HCl plus A minus. So what's going to happen? I can donate a proton. So hydrogen, instead of looking for water molecules to bond to, has this handy-dandy anion to bond to. So that means free electrons, and it's very attracted to it. So it's going to bond to my anion and form my weak acid. And then the chlorine ions, remember, we discussed that that's not going to make anything more acidic or basic. So if I look at this, what's going to happen is I'm going to end up with a whole bunch of my weak acids formed, and just a little hydronium floating around in my water. If I had added just HCl to water, remember that completely dissociates. So every mole of HCl would convert into a mole of hydronium. If I have my weak base, that anion is much more attractive to the HCl, or to the hydrogen atom, and so it is going to take up that bond. I'm going to produce less hydronium, but the weak acid is still going to produce hydronium nonetheless. So first I'll produce my HA, and then my HA reaction will go on to produce acid. So I am impacting the pH, but just not as much as I would have if I just added HCl straight to water. Now what about the same thing with a base? What is it going to react with? So let's come up with an idea for a reaction. I have my OH and my HA. what's going to happen here is my hydroxide is going to suck up one of those hydrogens. And as soon as it does that, I'm producing my conjugate base and water. So I am increasing by adding the base, but not as much. So remember before, if I did like sodium hydroxide in water, then I was producing all that OH minus. So in this case, I'm going to end up with like A minus plus water, and some amount of hydrogen is going to be attracted to that, and that's still going to produce my hydroxide. Equilibrium arrows. So that means I am still increasing my pH, but just not as much as I would HA. Not as much as I would if it was the strong base directly into the water, like a sodium hydroxide kind of base. And the picture shows the exact same thing. So essentially what we're doing is we're giving the strong acid and the strong base something to react with that in itself isn't going to dissociate as easily as the strong acid or the base. So still impact the way a strong acid or a base would as far as pH goes, but not to the degree. So I'm softening the blow of adding a strong acid or a base, and that's the benefit of a buffer. So let's see what that looks like. If I added a strong acid or a base, you can see the addition of the strong base. What do I have here? This is a change of 5, strong acid, a change of 5 in the pH, and the strong base does the same thing in the opposite direction, a change of 5. If I add a strong acid or a base to a buffer, my change is very small compared to the buffer's pH to begin with. So it still increased in terms of adding a strong base. You can see this like maybe 10th-ish, just visually estimating. And so that is the benefit of the buffer. And remember, there are certain biological systems that need to have constant pHs. So that's why these sort of systems are so important to understand. So how do we make one? We make one with a conjugate acid and its conjugate acid and its base, its weak base, or a conjugate base and its weak acid. If we have those two things in solution, then we're giving either our strong acid or our strong base something to keep itself entertained with other than water. So it diminishes the impact. Now the important part here, though, is there's only a certain amount that I can do that with. If I keep adding a strong acid or a base, eventually I'm going to use up my weak acid or a weak base, and then I am going to have the regular impact that I would have by adding either of those. So in small quantities, Henderson-Hasselbalch works only when we can ignore this change in X, and if the concentrations of both my conjugate acid or base and their weak acid or base are similar. They don't need to be identical, but similar. And that's just because if you come back to here and think about adding a strong acid or a strong base, that my buffer is going to have little impact if I don't have similar concentrations, right? So if I add HCl to something that has a minimal amount of my conjugate base, well, then HCl is going to use up what little of that conjugate base there is rather quickly, and the buffer impact isn't helpful at all, or it isn't going to change things much. My pH is going to go way down. All right, let's see how this looks applying it.